In this lecture, we're going to take a look at strain displacement in polar coordinates. Let's write down our setup here, our coordinate systems. Here's our x and y system. And we can identify some point out here that's at the angle theta, some distance r from the origin. And at that particular point, we can think that we have some displacements u and v in the x and y directions respectively. And we can also think of having some displacements in the r and theta directions. We'll call capital U and capital V. Now there's some relationships we're going to use. We wrote these down in the previous lecture, but let's go ahead and write them down again. We have cosine theta is equal to x over r. If we want theta, then we can take the inverse cosine of x over r. We are going to need the derivative of the inverse cosine. And this is an argument u, this isn't a displacement u. It's equal to minus 1 over the square root of 1 minus u squared times the derivative of u. We're going to have y is equal to r sine theta, x equal to r cosine theta, r squared is equal to x squared plus y squared, r equal to x squared plus y squared to the 1/2 power. And we're also going to use the partial derivative of r with respect to x. And that would be equal to 1/2 times 2x divided by x squared plus y squared to the 1/2 power. Let me make sure that's clear there. Now, we can write little u in terms of the capital U and V. Little u is equal to capital U cosine theta minus V, capital V sine theta. And little v can be written as capital U sine theta plus capital V cosine theta. Now epsilon x is the partial derivative of little u with respect to x. And by our rules of calculus, the partial of u with respect to theta, partial of theta with respect to x, plus the partial of u with respect to r, partial of r with respect to x. So let's take a look at these partial derivatives. Partial of little u with respect to theta is going to be, okay, we got partial of capital U with respect to theta times cosine theta. We're going to have u times the partial derivative of cosine theta, which is a minus sine theta. We're going to have a minus partial of capital V with respect to theta times sine theta. And then we're going to have a capital V times partial of sine theta, which is a cosine theta. Okay, the partial of u with respect to r is the partial of capital U with respect to r cosine theta. And then we're going to have a minus partial of capital V with respect to r sine theta, since the partial of cosine theta with respect to minus V times the partial of r times sine theta. Okay, we got all those terms in there. All right. So we can find an expression then for epsilon x. Okay, let's write that on the next page. All right, so we have those terms put together. And from the previous page, we can find that the partial of r with respect to x, works out to be x over r, which is equal to cosine theta. And in the previous lecture, we ended up finding that the partial of theta with respect to x worked out to be minus sine theta over r. Right. And by a similar reasoning as what we did for stresses, we can find our expression from sigma x. We can use that to recover an expression for epsilon r by taking sine theta equal to 0 and cosine theta equal to 1, where theta goes to 0. We can get an expression from this epsilon x expression for epsilon theta if we take sine theta to 1 and cosine theta to 0, which corresponds to theta of pi over 2 radians. And then we can also find an expression for gamma r theta by going through the process at length again. We need to take those partial derivatives as appropriate. But here we have epsilon r and so epsilon r then would be equal to, after all these manipulations, the partial of u with respect to r, which looks pretty familiar. Epsilon theta, it's going to look a little more interesting. It's capital U over r plus 1 over r, partial of v with respect to theta, capital V. And then gamma r theta is 1 over r, partial of capital U with respect to theta, plus partial of capital V with respect to r, plus v over r. So these are the strain displacement relations in polar coordinates. Alright, so the next thing we'll look at then is a couple solutions that are axially symmetric problems, and then we'll get to look at our plate with a hole.